Hello, Astronomy. Mr. Janowski here. This is the second video for the Chapter 1 slides I'm making. So this is like day 3 of class. And I'm going to try to go quickly because the last video I made for the slides, I got too far into detail. It took too long. And I feel like if I don't make these videos quick and bite-sized, then they won't be of any use to anyone. So going quickly, let's get started. So last time, we learned that there's a useful model that has all of the stars lying the same distance away from Earth on the inside of a giant dome. The name of that model is the celestial sphere. And again, this is just a model. This is not accurate. This is not an accurate representation of what's going on, but this is very useful for explaining what we observe. So this is not really true, but it's a very useful model. Are the stars in a constellation the same distance from Earth, in the same direction from Earth, or both? Well, they are always, if they're in a constellation, they're always going to be in about the same direction from Earth. They might actually be the same distance away, but there's no way of telling just by looking at them from the Earth. Um, so, yeah, in this picture here, you can see a person on Earth looking out this way, and on the celestial sphere, this person sees two stars that appear to be very nearby. But what is their actual three-dimensional arrangement in space? Well, this one's much closer than this one. So, yeah, on the sky, they're right next to each other. In actuality, they can be very far apart. They can be 10 times, one can be 10 times further away than the other, or 100, or 1,000 times further away. But on the sky, they look like they're right next to each other. Already, I'm taking too long. I'm going to go faster. So, another vocab term. Where does the sky meet the ground? That's at the horizon. So, the horizon blocks half of the celestial sphere. When you're standing on the Earth, you look up at the night sky, you can see half of the stars, and you can't see the other half because the ground's in the way. How many official constellations do astronomers recognize? There are 88 official constellations. And we'll talk about those in this part of the slides today. So, yeah, because the Earth is spinning on its axis, if you're standing still on the equator, so maybe you're down in Ecuador, which just sped by us, you're not really standing still. You're actually moving 485 meters per second, so about half of a kilometer per second, which translates to about 1,085 miles per hour if you're standing on the equator. If you're standing here in Bethlehem, if you look at how the globe is going, the biggest line of latitude around the Earth is the equator. Because we're more north, we're up around here. The circle we do every day isn't quite as big as the equator, which means we don't go as far in the same 24 hours. So we're not going quite as fast. But we're still going 352 meters per second, or about 787 miles per hour, which is weird. Right now, if you're sitting still, you're actually going 787 miles per hour to the east. So this is not obvious. It doesn't seem this way. That's because your chair is moving too, the ground is moving with you, the room is moving with you. So it's not obvious. And this wasn't obvious to ancient astronomers either. To them, it made a lot more sense to believe that the Earth was actually standing still and the whole sky was rotating around the Earth. And the planets and the stars and the sun were moving through the sky that way, which is not true, but it is what it looks like. So, this is why the celestial sphere is a very useful model. So, it looks like the stars rise and set. The stars don't actually rise and set. The stars aren't the thing that's moving. In reality, these daily motions of the sun and the stars are all due to the fact that the Earth is spinning on its axis. So the celestial sphere is basically motionless. So what do I mean by basically motionless? So if this were a constellation, maybe it is, I don't know what these stars, if they represent anything in particular, um, but over the period, even over like thousands of years or tens of thousands of years, these stars relative to each other would all seem basically locked in place. So over 10,000 years, maybe this star right here will move a couple pixels one way or another, and the other one will move. So they are actually moving, but incredibly slowly relative to each other. But on any given night, if you look up at the sky, it's going to look like some of the stars are rising and setting. So I have those things in scare quotes down here. Stars rise in the east and set in the west, just like the sun. The sun, of course, doesn't actually move across the sky. What happens is the sun basically stands still in a sense, and the Earth spins. And because we can't tell that we're spinning, it looks like the whole sky is moving around us and the sun is moving around us. So, yeah, the stars move across the sky at night. They move kind of slowly, though. So, if you stand here staring at a star and are trying to watch it move, it's going to be moving so slowly that you can't actually notice it. But if you look over to the east and you see a star that is maybe right above the treetops or something, and then 10 minutes later you look back, it will have moved a noticeable amount. Um, Same deal in the west. If something is just a little above the horizon towards the west, 10 minutes later, it's probably going to be below the horizon. So you can't stare at them and watch them move because they're moving too slowly. But over just a short amount of time, they do actually appear to move. So if we're looking at the celestial sphere, there are 2 points that do not seem to move. So if you're in the northern hemisphere, you're only going to see one point, and if you're in the southern hemisphere, you'll see the other point. These points are called the north and south celestial poles, and they lie directly above the north and south poles of the Earth. So the Earth is spinning on an axis. If you take that axis and just project it out that way, straight above the North Pole and straight below the South Pole, not that above and below and up or down are really meaningful in this kind of sense. Um, yeah, they will point to the North Celestial Pole and the South Celestial Pole. So here in Pennsylvania, in the northern hemisphere, stars appear to circle the north celestial pole in a counterclockwise direction. So if you can imagine facing north, you might see a star rise in the east and then go over the north pole. I'm sorry, the north celestial pole, and then set in the west. So that would look counterclockwise or anti-clockwise, as some European countries say it. In the U.S., we usually say counterclockwise, CCW. So here in the north, right now in 2020, and for the last 1,000 or so years, and for the next 1,000 or so years, there happens to be a fairly bright star that just happens to be right about at the north celestial pole. This is Polaris, the North Star. It's in the name, Polaris, pole star. So from the north, from the northern hemisphere, stars seem to circle Polaris. So up there at night, there's Polaris, and the stars seem to go around it. Now, if you're in the southern hemisphere, there actually isn't a south star. It just happens that there's no particularly bright stars very close to the south celestial pole, so there is no south star the way that there is a north star. And real quick, somewhat useful, from Pennsylvania, throughout the year on any clear night, you should be able to see the Big Dipper and you should be able to see Polaris. So if you want to find the North Star, find the Big Dipper. This does actually look like a giant ladle. And look at the front two stars of the bowl part of the ladle. And if you draw a line through these stars uh, going in the right direction, you'll get to Polaris. So it kind of looks like Polaris wants to fall into the bowl of the Big Dipper. So yeah, if you can find the Big Dipper at night, you look up, you should be able to find the North Star. And if your phone is dead and you ain't got a compass, now you know which way north is. So another important thing on the celestial sphere is this thing called the celestial equator, and this lies directly above the Earth's equator. So look in here, you see the Earth spinning on its axis. If you went to the equator and just blew the equator out in all directions, what you would get is this circle on the celestial sphere that is the celestial equator. So stars that are on the celestial equator will rise due east and set due west. So whatever stars those are going to vary night after night depending where you are on the Earth. But if on that particular night there happens to be a star on the celestial equator, it's going to look like it rises due east and sets due west. If from the north, you've got a star that's north of the celestial equator, it's going to rise in the northeast and it's going to set in the northwest. And if it's south of the celestial equator, it will rise in the southeast and it will set in the southwest. And they won't none of these stars will necessarily go directly overhead. That depends exactly where you are and what star we're talking about. But yeah, that's the celestial equator. So I said the stars rise and set. That's actually not completely true. Some stars will seem to rise and set, and other stars won't. So if you're in the northern hemisphere and you look up at the sky and you see Polaris, well, we'll start with Polaris. Polaris, first of all, doesn't rise or set. It doesn't start below the horizon, pop up in the sky, and then go back down again. Polaris doesn't do that at all. The way Polaris works is, say you're out watching some beautiful sunset and you watch the sun go down and you're looking up at the sky. Uh, the sky will get darker and darker until eventually you can see the stars. And then all of a sudden, you'll see Polaris. And Polaris will be just right there. And Polaris is not going to move at all the entire night. It's going to sit right there in the sky, motionless, until however many hours later, until dawn comes. It'll get brighter and brighter outside. And then eventually, you won't be able to see the stars again. But Polaris doesn't move. So Polaris doesn't rise or set. It just all of a sudden, dark enough you can see it, and then eventually it's too bright for you to see it anymore. So the stars that are very near Polaris don't seem to rise and set. They'll just fade into view when it gets dark enough, do a little bit of an arc around the sky, and then look, it's dawn again, and now it's too bright to see the stars anymore. So these haven't risen or set at all. They have nothing to do with the horizon. So it's a little hard to see in these pictures. I'm sorry, at least in this picture. This picture's a little closely cropped. But yeah, it's the other stars all the way out here to the outside. So some of these stars would appear to rise. At night, it's dark, and then you would see the star rise above the horizon, do part of a loop. And while it's doing that, other stars are sinking below the horizon. And there are other stars, remember, because the horizon blocks half of your view. So half of the stars in the night sky at any given time, you won't be able to see because they'll just be below the horizon. So yeah, if we're looking at this picture here, so image A over here to the left. So here you are out on this old ship. I don't know, maybe you're a pirate. So yeah, Polaris would be there the entire time. These circumpolar stars would do this loop around the sky like this. If a star were on the celestial equator, it would start due east, do a loop, and sink due west. Other stars would do different loops. And if the star is down here, yeah, it would never actually rise above the horizon. So those are the daily motions of the sun and stars, and those are all due to the Earth's rotation on its axis. So if we were actually there in class, I would pick up a globe at this point and spin it and show you that, yeah, the Earth is spinning on its axis. Hopefully you know this by now. So those are the daily motions. The daily motion is the Earth spinning on its axis. And we call this motion rotation. So the Earth spinning on its axis is rotation. There are other motions, they're called the annual motions of the sun and stars. And these are due to the fact that the Earth is actually going around the sun. So, yeah, you can think of the daily motions and the celestial sphere. It gets a little more complicated when you're thinking of the annual motions. So the word for this is revolution, revolving. So we say the Earth revolves around the sun. The Earth rotates on its axis, but it revolves around the sun. So in plain English, those words, rotation and revolution, might just be synonyms, but in astronomy, we always use them for this. The Earth rotates on its axis, it revolves around the sun. So the revolution is the Earth doing laps around the sun, is what a revolution is. And those revolutions lead to what are called the annual motions of the sun and stars. So yeah, this picture is a little complicated. So we're only looking at a little band of constellations going around the Earth around what's called the ecliptic. I'll get there in a couple of slides. So we're not seeing all 88 of the constellations. We're only looking at about 12 of them right here. So how does this work? So if you looked at the night sky in early July, you might see Scorpius. So check out the image. You've got the sun in the center. Um, I'm not even aware, because sometimes it gets recorded and sometimes it doesn't with Screencastify. I'm not even aware if you can see my cursor. But if you can, I'm pointing at things. So here's the Earth in June. Here's the Earth in August. So yeah, July, it'd be right in this area right here. So in July, in the middle of the night, you look up in the sky and you can see Scorpius, and you can see Libra and Sagittarius. You can see all of these things. About 6 months later, when we're over here, you're not going to see Scorpius, Sagittarius, and Libra at night because those stars would be up during the day. But of course, during the day, the sun lights up the whole sky, and you can't see those stars during the day. So, yeah, when we're here in our orbit, you can see Scorpius in the middle of the night. 6 months later, we're over here. Scorpius is still where it always is, but it's up during the day, so you don't see it. In the middle of the night, 6 months later, you're going to look up, you're going to see Gemini. And Orion, which is not on here, but Orion will come into view and things like that. And then 6 months after that, the Earth is back here, and lo and behold, you can see Scorpius again, and you can't see Gemini. You're going to have to wait a couple months until we get to a point where you can start to see Gemini at night. So these are the annual motions. And this is what I just said. Yeah, the stars on the celestial sphere, they stay put. Which stars you can see on any given night are going to depend on where the Earth is relative to the sun. Um, so yeah, the stars that you would have to look past the sun to see, yeah, you're not going to see those because that's called daytime. You'll see the stars that are behind you, that are opposite where the Earth is to the sun. Those are the stars you'll see at night. So how does this work? This should get the astrologers interested. This is what it means to be such and such a a star sign. Although I'll have more on that at the end. Um, Spoiler alert: I'm going to crap on astrology a little bit today, and also just throughout the entire year. I really don't like astrology. So anyhow, if we're here, the Earth is here in June. If we drew a line from the Earth through the sun onto the celestial sphere, it would pass through Taurus. So, what does that actually mean? So, here we are. Imagine it's June 1st. You're watching this beautiful sunset, and then the sun goes down and it starts to get darker and darker. If you keep looking in the same direction, you're going to see that where the sun sets, the constellation that appears is Taurus. So, we would say that the sun is in Taurus on that night. That's what that means for something to be in such a constellation. So you just sit there all night long. You've got nothing better to do, and you wait until dawn. If you keep looking at Taurus, great, yeah, Taurus is there, and then eventually dawn will start to happen, and the sun will start to rise, and it will rise in Taurus again. So it will set in Taurus at dusk, and then however many hours later, it will rise in Taurus again. Now, notice if you wait about a month, so now the Earth is here. If you were looking through here, you wouldn't see the sun rise and set in Taurus anymore. It would rise and set in Gemini. So Taurus is now below the horizon, and Gemini is where the sun seems to rise and set. Um, and the stars on this little loop, this is called the zodiac. They just keep taking each other's place and moving in line, going around and around. And then finally, a month after that, we're here in August, and we're gonna watch the sun set, and the sun will seem to set in Cancer, and then the next morning it will seem to rise in Cancer, and it just goes on and on like that. So little thing that's a little bit weird. If you consider the Earth's daily motion and its annual motion at the same time, the way these guys interact, it turns out it doesn't actually take 24 hours for the Earth to rotate 365 degrees. It's a little bit weird. So because the Earth is spinning, so if we look at the image to the left, has the Earth it's spinning and it's moving at the same time. Um, so 24 hours later, it's not going to exactly line up with the sun again. It's because the Earth has moved a tiny little bit, and that difference ends up being about 4 minutes, 3 minutes and 56 seconds. And over the course of the year, 3 minutes and 56 seconds times 365 days adds up to 24 hours. So basically, the Earth returns to the same place year after year, and the sky looks basically exactly the same on the same date year after year. It gets a little bit more complicated than that, but that's basically what's going on. So yeah, let's start this time. Let's start in August. So yeah, August. You're going to see the sun rise and set in Cancer, and then in the middle of the night, if you look straight up, you would see Capricorn. And then 3 months later, you're over here. You're going to see the sun rise and set in, I think this is Libra. It's cropped off my page right now. And then in the middle of the night, if we were here, you would look up, you would see Taurus. Another 3 months, the sun would rise and set in Capricorn. The Earth would be here. So the sun would rise and set in Capricorn. And in the middle of the night, you would see Cancer. So we started with the sun in August, with the sun rising and setting in Cancer and Capricorn up in the middle of the night. 12 months later, we're back where we started, and you have the same thing happening. The sun will again rise and set in Cancer, and Capricorn will be up in the middle of the night. I mean, it'll be like straight overhead in the middle of the night, basically. So the sky thus provided a very important calendar for ancient civilizations. Now we just use calendars. But before anyone actually figured out how long the year actually was, they were using the stars. So again, think not only did they have way less light pollution, so they had a beautiful view of the night sky, which got them more interested in the stars, but it was actually very important culturally what the stars were doing. So all these ancient cultures, all their ancient priests and priestesses and temples, this was part of their job, was knowing what stars rise and set at different times of the year, and being able to tell you what's going to happen next. So just as an example, uh, if you were living in ancient Egypt and you looked for Sirius near the sun just before dawn, when that started to happen, that would tell you that, oh yeah, it's that time of year when the Nile's about to flood again. And then a little while later, when Taurus was visible just before dawn, that means it's time to plant your crops. So yeah, what stars were up at different times? That was the original calendar that we used. So we have this important vocab term, the ecliptic. So if you could mark on the celestial sphere the path traced by the sun as it moves through the constellations, you would see a line that runs around the celestial sphere. So what does that really mean? So if you look at this picture, and this is, not to scale, but this is about what's happening. If you look at this picture, the background stars are basically motionless. They're not really moving. And their apparent motion is due to the fact that the Earth is moving. So if we're here on Earth, and this is over the course of, about 6 months as we do this half circle here, it looks like the sun is moving across the background stars. And if you were to follow that for a whole year around and trace the path of the sun around the background stars, that is one definition of what the ecliptic is. It's not the only definition, but it's one that's true and it works. It's the apparent path of the sun across the celestial sphere. You may have noticed that the name ecliptic sounds like eclipse. Well, they're very much related. You only get uh, solar eclipses and lunar eclipses when the moon happens to cross the ecliptic, which isn't true month after month, but sometimes it does. And that means you're going to get one or both kinds of eclipses that month. So, yeah, that's the ecliptic. That's one definition of the ecliptic. So, here is your other definition of the ecliptic, which ends up being exactly the same thing. We're just thinking of it a different way. So your big circle, that's your celestial sphere. The sun is actually right here in the middle. This is more accurate. And the Earth is going around the sun. So the Earth is doing its orbit, and it's doing its orbit in this plane. So, like, yeah, math class geometry, this is a plane. So the plane of the Earth's orbit, if you extend that out in all directions, that is also the ecliptic. It ends up being the exact same thing as imagining it. Well, it doesn't look like it like that. As imagining it has the path of the sun, um, but it's really the exact same thing as the Earth's plane of orbit. So again, how many constellations are there? There are 88 official constellations. Most of them are going to be above or below the ecliptic. So it's only the ones, if we look at this picture, yeah, we've got these that are in the plane of the ecliptic. So this dotted blue line around here is the ecliptic. And most of the other constellations are above it or below it. So the sun is never going to appear in most of the constellations. There's only a set number of constellations that it ever appears in. So how many constellations does the sun appear in each year? About 12. You astrology fans would love it if it were exactly 12, but it's not 12 actually. It's actually 13. But yeah, we say 12. This leads to months. This is one of the things that leads to months. So yeah, that band of 12-ish constellations that the sun ever appears in, that's what the zodiac is. So, what does zodiac mean? Um, it's from the Greek zoidion, meaning little animal, zoidion, like zoo animal, and kyklos or cyclos, circle. Put those words together, you get zodiac. And Again, out of the 88 constellations, the sun does not appear in most of them. It appears in about 12 of them. It's actually 13 is the exact answer, but I'm calling it about 12. So, much to the dismay of the astrologers, the constellations of the zodiac they're randomly placed, basically. Well, all the constellations are randomly placed, but the 12 that are in the zodiac, they're not equally sized and they're not very equally spaced. Um, So they don't divide the year up into 12 equal periods. And in fact, the sun spends part of each year in this other constellation that none of the astrologers like, Ophiuchus, which is the snake charmer. And it's actually cooler than most of the other ones. But I'm going to tell you that none of it means anything. And another little thing that's messing this all up. So the Earth, as it goes around the sun, it keeps its axis pointed pretty much in the same direction, in almost exactly the same direction, but not quite exactly. Um, so yeah, as the Earth goes around the sun, so for example, here we are in February. This is northern winter. The Earth's axis is going to be pointing out away from the sun in this direction. Um, yeah, I hope you can see my cursor, and it's pretty much always pointing off in that direction. So up and to the left, way off in the distance is where it's pointing. So in May, it's still pointing in that direction, up and to the left. In August, where it's pointing vaguely towards the sun, at least a little towards the sun, up and to the left, and like this. And it basically maintains that, but again, not perfectly. So over thousands of years, it's like 25 or 26,000 years or so. The angle of the Earth's orbit does a full rotation. Um, Not all at once. It does this very slowly over 26,000 years or whatever the number is. This is called precession. So you can think of this if you imagine spinning a little top. So the top is now spinning around. So the top, when it's going real fast, will point pretty much straight up. But eventually it's going to start to wobble. And the axis it's spinning on is going to start to do loops as the whole thing is spinning itself. That is what precession is. So, what does this mean? It means that over thousands of years, the Earth's orbit changes a little bit, and it's not always pointing the right way. And what is the North Star now in 2020? It wasn't always the North Star, and it won't always be the North Star. We're going to get something else. And then 26,000 years or 24,000 years later, yeah, Polaris will be the North Star again, all in this very cyclical way. So, why am I bringing this up? Because the Earth's orbit changes over thousands of years, and because this thing called astrology was originally invented um, thousands of years ago, the traditional astrological dates aren't even the right astronomical dates. When people thought this up, they would say things like, okay, you're born on May 21st. That makes you a Taurus because the sun was rising and setting in Taurus on May 21st, which was true thousands of years ago, but it's no longer true because the Earth's orbit around the sun and the Earth's axis of rotation slowly changes over time and it drifts and it wobbles a little bit. So the upshot of this is that most people's astrological sign, if you know it and it's important to you, um, is actually a month off from what it really is. And I'm going to tell you that it doesn't mean anything either way, but it's worth knowing. So, for example, my birthday is October 19th. So most people who do astrology would tell me that, okay, October 19th, that means I'm a Libra. That's not actually true because on October 19th, I mean, I know this is what it says here. On October 19th, if the day I was born, okay, I've got it backwards. This graph is not agreeing with this chart. What actually happened on October 19th, the sun was rising and setting closest to Virgo. So, yeah, these are the traditional astrological dates, broken up into 12 fairly even, periods. All these months are about the same length, or all these signs are about the same length in time, which was actually never true because the constellations aren't equally sized. But yeah, these things were started thousands of years ago. In the thousands of years since, because everything has drifted, um, yeah, when the day I was born, October 19th, 1976, the sun actually rose and set in Virgo. So I'm a Virgo. I'm not really a Virgo. I'm not really a Libra. This is all nonsense. I don't believe in any of this stuff, and I don't want any of you to either. Um, but yeah, it's all drifted. So yeah, if you love the astrology, do me a favor, look at this chart, find what date that you think you are, and then compare it over here. And I love this, and the astrologers hate this. I'm being way too negative about astrology right now. It's kind of, I'm doing it to a fault, but whatever. I got to be me. If you happen to be born between November 30th and December 17th, you're going to be telling everyone that you're a Sagittarius. That's not true. If you're born on those days, you're actually an Ophiuchus or an Ophiuchian or whatever it's going to be, because most of these things have drifted. There are a few people who get to keep their signs, but most of them are off by about a month. And you'll notice too the lengths of the actual days that the sun rises and sets in those signs. Yeah, it's all over the place. Some of them are about a month. Gemini is about a month, but Virgo's really long. Virgo's 45 days out of the year. Um, Scorpius. Yeah, I bet you 1/12 of you think that you're Scorpius. That's not nearly correct because the sun only rises and sets in that constellation 7 days out of the year. So it's a very tiny, it's less than 1/50th of you are actually Scorpius. So, yeah, that's how that works. I'll stop harping on this. So, yeah, quick review. What useful model has all of the stars lying the same distance from Earth in on the inside of a giant dome? That's the celestial sphere. If you see a constellation, are the stars in that constellation the same distance from Earth, in the same direction from Earth, or both? The only thing you can say for sure is that they're in the same direction from Earth. They might be the same distance, but they might be completely different distances. And what causes the daily motion of the sun and stars? The daily motions are caused by the rotation of the Earth on its axis. So, for observers in the northern hemisphere, do stars appear to circle the north celestial pole in a clockwise or counterclockwise direction? Um, Counterclockwise from the north. So, yeah, they go around, the stars go around Polaris counterclockwise. So, if you looked at Polaris and imagine Polaris as the center of a clock, um, the stars would move from 3 to 2 to 1 to 12. They would go against the clock. So if a star is close enough to the North Star, it won't appear to rise or set, but rather stay up all night. What do we call such stars? We call them circumpolar. So yeah, here's Polaris right in the middle. Moves a tiny bit, but basically doesn't seem to move through the night sky. It basically just sits still. All the other stars that we can see from the north rotate around Polaris. So yeah, there's a quiz on Google Classroom. Take the quiz. Take it as many times as you need to get the grade that you want. And next class, we'll start off. We'll do the Kahoot. Maybe we'll watch this video. We'll see. So yeah, I intended to make this short. It ended up being long, I'm sure. But hopefully you guys found it helpful.